welcome to my YouTube channel. This is Unit 2 Current Electricity, and today we are going to develop the relation between current and drift velocity, that is the velocity with which electrons drift from one end of the conductor to the other end. So let us define the value of current. We know that current is defined as rate of flow of charge, that is I is equal to Q upon T, and where Q is representing the total charge which will flow through the metallic conductor divided by the time, that is the time in which this charge will flow through the metallic conductor. So this is our equation number 1, which is the core equation which will help us to develop the relation between current and drift velocity. Now we have to consider a metallic conductor because we have to calculate the total amount of charge which will flow through the metallic conductor in a certain interval of time. So let us consider a metallic conductor such that this metallic conductor has a length L. So let us mark the length of this metallic conductor as small l, and we can say that the area of this metallic conductor is equal to capital A. So area of this metallic conductor is A. As we know that in metallic conductors there are always free electrons which will contribute to the flow of current. So this metallic conductor is connected across the battery because we need to provide the potential difference in order to make the electrons drift from one end of the metallic conductor towards the other end. As soon as we will attach this metallic conductor with a source of EMF, the electrons, these free electrons, will start drifting with the velocity Vd from one end of the metallic conductor to the other end of the metallic conductor. So let us say we are having small n number of free electrons present in a unit volume of this metallic conductor. So if we are having small n number of electrons present in a unit volume, we need to calculate total number of electrons, total number of free electrons. That means we have to calculate the total volume. So here in this case, total volume of the metallic conductor is given by area into length. So AL is the total volume of the metallic conductor. Now we are having total volume. We know that n number of electrons is present in unit volume. So therefore total number of electrons present in total volume is given by number of electrons present in a unit volume, that is n, multiplied by total volume of the metallic conductor, that is AL. That is n into AL are the total number of free electrons which are present in this metallic conductor. And the question is why I have calculated this much, because I was interested in finding the value of charge, as the equation is I is equal to Q upon T. So we need to know what is the total amount of charge which is going to flow from one end of the metallic conductor towards the other end. Therefore we know Q is equal to number of free electrons flowing multiplied by charge on one electron. So this is the total charge flowing through the metallic conductor. Thus we can say the total amount of free charge which is going to flow through the metallic conductor is given by Q is equal to total number of free electrons in the metallic conductor, that is NaL, multiplied by charge on one electron, that is small e. So Q is equal to NaLe is the second equation. Now this is the second step which we have covered to find the value of charge, and now we need to find the value of time. That is, we need to determine in what time these free electrons will move from one end of the metallic conductor to the other end. So in order to find the value of time, we have to recall the definition, that is time is equal to distance upon speed. Here the free electrons are going to cover a distance that is equal to length of the metallic conductor, that is our electrons are going to move from one end. Let us say they are going to move from the A end of the metallic conductor to the B end, and as the charges are going to drift from A to B end, they are going to cover a distance that is equal to length of the metallic conductor L, and these electrons are drifting with the drift velocity Vd. So time t is equal to L upon Vd, which is our equation number 3. Now we are going to use these two equations, equation number 2 and equation number 3, in equation number 1. So we are having I is equal to NaLe divided by L upon Vd. Now rearranging this equation, we are having I is equal to NaLeVd divided by L, and we can cancel out L over here, so we are left with I is equal to neAvd, where N is representing number of free electrons in a unit volume, E is charge on one electron, capital A is representing area of metallic conductor, and Vd is representing drift velocity. So current is directly proportional to the drift velocity. Now from this expression we can easily find out the Ohm's law. So this is again an important point to know, that how we can determine the Ohm's law from the relation I is equal to neAvd. We will start from this relation only because we are going to deduce Ohm's law from this relation. So what the first step which we can use is that we can substitute the value of drift velocity. So in the previous article we have learned that Vd is equal to minus EE upon m into relaxation time. So in terms of magnitude we can say Vd is equal to small e capital E divided by m into relaxation time, where m is representing mass of electrons, therefore we will put the subscript E. Now we will use this value of drift velocity in the relation I is equal to neAvd. So I have written I is equals to NEA, and instead of writing Vd I will put the value that is EE upon ME into relaxation time. So now we can rearrange this equation, we can multiply small e, so we have I is equal to NE square A capital E relaxation time divided by mass of electron. So in this expression we are not having potential difference, and in Ohm's law we know V is equal to IR. It is the relation between potential difference and the current. So here there is no potential difference present, therefore we have to recall the definition of potential gradient, that is E is equal to V upon D. Here from this equation E is equal to V upon D, we can easily find the value of potential difference. And now in case of metallic conductor we have taken the length of metallic conductor to be L, therefore we will use E is equal to V upon L, and we will put it in the equation I is equals to NE square A capital E upon ME into relaxation time. Therefore we are having I is equals to NE square A into relaxation time divided by ME, and instead of writing capital E I have substituted V upon L. So this is the expression, and this expression needs to be modified once again. We will rearrange all the things at the certain points. So we have I is equal to NE square, and instead of writing A I will write a relaxation time divided by ME, and I will separate out A upon L, and whole thing is multiplied by potential difference V. So now cross multiplying this equation we are having I is equal to V is equal to I into MEL upon NE square tau. So here in this equation we need some more modifications, and we will put ME, that is ME, which is the mass of the electron, multiplied by L upon NE square A relaxation time is equal to R. When we will put these things in the equation, our equation will turn out to be V is equal to IR. So this is the expression for the Ohm's law, and this expression is relating potential difference and current. Now this is our Ohm's law. And we have to consider one more thing, that is our value of R, which is equal to MEL upon NE square A tau. Now in this equation R is directly proportional to L and R is inversely proportional to area, and we already knew this thing as we have learnt it in class 10th. Therefore we are having R is proportional to L upon A. So that means we have substituted the right term. And I hope now you have understood this concept. If yes, then do not forget to press like, subscribe and share button, and do press the bell icon in order to get the latest notifications on my videos.